Is it okay if you just jump in?
Yep, no worries. All
Thank
right, I'll just get going. All right, okay. So, yeah, talking to you about cryomineralogy, which, see how that goes. I didn't even get very far, but this is my outline of my talk. As I said before, I'm a crystallographer, and I thought I'd also tell you a little bit about how we take powder diffraction data and turn it into crystal structures as well. So I really like patterns. It's something that I've really enjoyed for a long time. I've knit a bit and things like this. And I was thinking once about where my enjoyment of patterns came from. And as Garrick said, I grew up in England, just to the east of London. And I used to ride the underground all the way into my grandparents lived right at the end of the district line, which is the long green line, if you've ever looked at the tube maps. And used to go, and then the other end of it is the Natural History Museum, which was the place with all the cool minerals and the rocks and things. So you can see a pattern there already. And I used to spend, it's about 45 stops from Upminster through to South Kensington. And I used to stare at the pattern seats and sit there and work out what the repeating unit of the pattern was. Later, I actually went as an undergraduate to London, and I was delighted to find that every tube line has a unique pattern. You can see a proper nerd going on here. And so I sat there and through my undergrad worked through all the different units of the patterns. So it turns out that what I learned in my fourth year of my undergraduate is actually that, this isn't too different to being a crystallographer. And essentially that's what I do now for a job. But instead of doing it on seat covers of tube trains, I take the three-dimensional diffraction patterns that we get off of all sorts of any crystalline material. And then I'm able to work out the crystal structure from that. But even if I can't work out the crystal structure, just being able to get the Bragg scattering from that, even looking and tracking that as terms of different temperatures and things like this, that can also give us a lot of information, and I'll talk to you a bit about that later. So behind me, for instance, is the diffraction pattern of tripalmitin, which is a very, it's a long chain fatty acid. It's an important one because it's one of the ones that you find in chocolate. So where am I actually these days? So I'm based in Australia at the Australian Centre for Neutron Scattering, and this is part of ANSTO, which stands for the Australian Nuclear Science and Technology Organisation, and we're one of the government science agencies in Australia. You might have more likely have heard of CSIRO. They're a little bit more famous than us. We actually run Australia's only nuclear reactor, and it's a research reactor, so it's not a power reactor. And we mainly run it for medical isotopes, but we also have a number of neutron instruments sort of attached to it, and I'll talk a bit about them. So ANSTO has recently become sort of the running of the big facilities in Australia. So for like in America, where you have like NIST and APS and the Berkeley, the Advanced Light Source in Berkeley. And Australia, we have the Australian Synchrotron. We have a Centre of Acceleration study, Centre of Accelerator Science, and we also have the Australian Centre for Neutron Scattering. So this is sort of an additional thing that ANSTO has sort of moved into. And as you can see, we're sort of located just to the south of Sydney, sort of the airport's here in Botany Bay, and then there's the CBD there. So you can sort of just picture where we are, and we're sort of just covered in trees everywhere. So we're very much buried in the bushland out here. So as I mentioned, that we've got about 15 instruments that come off the nuclear reactor, and you already probably noticed the slightly cute thing is that we name all of ours off of after Australian animals. So I'm actually technically a wombat scientist, and I'm also run Echidna, and these are our two powder diffraction instruments, although wombat is able to do quite a lot more as well. And then each of these instruments will look at different length scales and different types of materials, from our big instruments, which are like our small angle scattering, through to Dingo, for instance, which is our instrument, our imaging instrument. So just to give a bit of an idea of how we analyze our powder diffraction, so we throw neutrons, and you can actually do this with X-rays. And on one back, we actually get a two-dimensional image. So this is like the two-dimensional image we get. So we can actually look at samples that aren't perfect powders as well. And one of the things we do, and hopefully it will come up at some point, is that we actually collapse that down to a one-dimensional trace, and that's our powder diffraction pattern. And one of the things that we sometimes go on to do after that is then stack them up as we change the temperatures. So in my case, there's a nice example of that. So that's I've collapsed there the one-dimensional, the two-dimensional image to this one-dimensional pattern, and then I can go on, and the fitting of this is something that is really quite straightforward, that any sort of laptop can cope with without too many problems, although tripomatin's quite a complicated structure actually. So I mainly these days scatter neutrons, but of course you can undertake diffraction with X-rays and with electrons as well. I don't personally do much electron scattering. It's not so useful for these sort of cryomineralogical materials, but X-rays we do a lot in terms of, because they're much higher resolution, so we're able to really find the structures from them. But then neutrons are brilliant because X-rays scatter dependent on the amount of electrons in the cloud. So hydrogen, carbon, oxygen, all of the main elements are not actually particularly well scattering. And so one of the really nice things is that neutrons actually do scatter much better from these elements, and so we're able to get a lot more information from them sometimes. So it's sort of a nice pairing of both of them. So that's a bit of an introduction of what I do. I think this is not going to be a controversial statement, hopefully. The solar system is an awesome place. And one of the things that has inspired me for many years is quite how different it is as we go, from the terrestrial planets all the way through to the gas giants and all the icy moons. And as you can see, I'm actually reminded of this quite a lot. This picture was taken by my partner, and these are just pictures that we can, well, not just pictures, he does a lot of work to make them this pretty, but these were all taken from our backyard in Sydney. But as Garrick said, that I've really focused into ocean worlds, and one of the things I really like about them is how diverse they are, how different their landscapes are, but and how this is driven by different materials that make up those surfaces. So from the bright spots that we see on Ceres to the recent reports of glowing Europa, the lakes on Titan, and the glaciers of Pluto. These are all happening, as we all know, with materials that are not the traditional sort of rocks that we would expect these sorts of effects happening on our terrestrial planets. And there's a lot of knowledge still to be gained about how those materials actually work. So we've recently dubbed this sort of study of these materials as cryomineralogy. So I've sort of been stumbling around mineralogy for a number of years, and those of you who are maybe not familiar with it, it's a subject of geology that specializes in sort of the chemistry, crystal structure, and physical, including optical properties of minerals and mineralized artifacts, which is good because it covers opal, which is not, and from my 2 cents, not a mineral because it hasn't got a crystal structure. So one of the things that we've so a natural place to publish a lot of this work is mineralogy journals, because essentially that's what we're trying to do. But we've sort of bumped into this a few times because mineral actually only refers to a naturally occurring material on Earth. And so a lot of these materials that we've studied wouldn't solidify necessarily on Earth, but of course do on the outer solar system, and are sort of very important in terms of sculpting them. So recently the American Mineralogist has actually redefined their journal. They now call themselves the Journal of Earth and Planetary Materials. So I feel like we're having some headway, but and I'm not sure I'm too worried about all of these materials I'm looking at getting mineral names as such. But the important thing, the interesting thing is that though we go from all of these materials can do sort of the traditional things that we see materials, anisotropic thermal expansion, complicated crystal structures, substitution, and things like this. but they have a bonus in that they can actually make do many other things that the traditional silicate minerals that traditional mineralogists look at can't. So these are phenomena such as plastic crystals, order-disorder transitions, pyroelectricity, and polymerization. So all of these are processes that can happen with these small molecules that do not happen with traditional minerals. And so I'll touch on a few of these properties as we go through. So I've mentioned a lot about them in general terms, but what actually are these materials? So around the asteroid belt, we're talking about carbonates and sulfate hydrates and some small organic molecules. When it comes to the Galilean moons, water ice, ice 1H becomes very important. In fact, probably amorphous ice and maybe high pressure ice is further down as well. Chloride hydrates, so NaCl plus water, have become very important, and sulfate hydrates, and I'll talk a bit about some of the work I've done there. And then when we get to Titan, I'll talk a lot more in detail about Titan, but we've recently sort of defined them into 3 different types of materials, so molecular solids, co-crystals, and gas hydrates. And then as we go further out to the Pluto and the Kuiper Belt objects, we have things like nitrogen, methane, and carbon monoxide that become solid and are the sort of the materials that shape the surfaces there. So how do we go about actually understanding this? And I've talked a little bit more about, introduced a lot about the technique that I've been using recently, the X-rays and the neutrons, but I work a lot with the IC Minerals group at JPL, who do a lot of Raman as well. And so this is sort of our workflow where the Raman often will discover new structures or indicate that something would be there. And then we follow up with X-ray and neutron scattering experiments. And then sometimes it's sort of some of the topics sort of take their own form, and we'll do a bit more different types of neutron scattering, some inelastic work and things like this to really drill down and find the most that we can. So in terms of a sort of workflow, the first job is always to find the crystal structure. Without the crystal structure, you're sort of flailing around quite a bit. Of course, we're very indebted to theorists in instructing us and helping us find what might be interesting to look at. But the problem is a lot of these materials is they are often disordered, and that makes it a bit of a challenge to model these systems. And then we start to look at the physical properties, and then lastly we're trying to look at the mechanical properties as well, so trying to put these in context of the surfaces. So as a first stop, how we're doing for time, yeah, doing all right, we'll stop at Europa, and this is sort of the work that I've sort of started when I moved to Australia and started to sort of wander a bit. And the surface of Europa is obviously an interesting and slightly dangerous place. And although we are very interested in it because of the potential life-bearingness of the ocean below, our biggest clue to the composition of the ocean is, of course, the surface. And then, of course, there's a number of theories that have come as to what the materials actually are and what are the processes driving those materials. And there's sort of like these 3 main theories are the materials. So we have a dominant of water ice, but of course, as you can see there, there's a lot of materials there that aren't water ice. You can just see that from the color and the way that this color is also correlated with things like the cracks there as well. So there's the big theory that a lot of it is the radiolysis of iosulfur, so sulfate that comes from Io's volcanoes that smacks into the surface and actually starts grabbing hydrogen and oxygen from the water, becomes sulfuric acid, and then to form hydrates from that. Recently, we've heard a lot about radiation damage that could be things like sodium chloride that undergo radiation damage that causes color centers. But then, of course, we've got this idea that we could get material from an ocean. And as Hubble has now confirmed that we see geysers from Europa, that's definitely a potential process as well. So you can sort of divine these two into both exogenic and endogenic, the radiation damage of endogenic materials being a combination of 2. And this is sort of something that's really fascinated me for a wee while. One of the things that started this was actually reading that sulfuric acid octahydrate, which was meant to be one of the most dominant materials and still is a recent reanalysis of the Galileo NIMS data sort of again suggested that sulfuric acid octahydrate will be a major material on the surface. But when I actually looked at the literature back in 2011 when I started this, there was actually papers that published that suggested that sulfuric acid octahydrate didn't actually exist, which was slightly surprising. So me as a new postdoc at the Australian synchrotron at that time, not having a great deal of money, I was like, well, if I just take some water and some sulfuric acid, I can cool it down and see what crystallizes. I say I didn't have much money, but I did have a synchrotron beamline at my disposal. And so I did that and was able to find the sulfuric acid octahydrate, looked at the structure. But one of the things you can see from here on this top image is you can see this is a typical diffraction pattern I got. I did a number of compositions. But you can see there's some missing peaks. So the green line is my model from the sulfuric acid octahydrate. And there's those black ones that aren't being modeled suggest that there's something else there, that there's a different phase. And playing around with the compositions, and you can see that one of the nice things about the synchrotron, we get very high resolution data, so we can go forward and solve the structure, is I discovered that there's actually another form, sulfuric acid hexahydrate, so slightly less water in the crystal structure. This has probably been one of the reasons that people have struggled to pull out the spectral data, because probably whenever you're crystallizing octahydrate, you're also getting the hexahydrate as well. And one of the reasons behind this is actually how similar their crystal structures are. They both have the same layers all the way through them. So these sort of water layers come through, sort of put like dotted lines that show the hydrogen bonding through them. I always describe this one, sulfuric acid octahydrate, as a peanut butter sandwich, where the sulfate is like the peanut butter, and sulfuric acid hexahydrate as a peanut butter and jelly sandwich, where it actually has hydroniums within the structure as well. But the nice thing about them is that we can start to think of these, and somebody once suggested I call them this, and I didn't go that far, as like, they're like the phyllosilicates, they're like the layered clay structures that we see on Earth to some extent. So someone suggested I call them star clay, but I'm not entirely sure about that. Maybe planetary or icy clay would be more appropriate. And the thing is, automatically you can see that if you've got a sort of lump of Europa, which is made out of some of its water ice, hexagonal water ice, which is actually really strongly bonded, it's quite well, disordered, but can be really, really strong. And versus these materials, which are more layered, you've automatically got a big change in their mechanical properties. And so that can drive potential formations on the surface there. We've taken this to the next sort of level and began to look at some of the other components. So magnesium sulfate hydrates and sodium sulfate hydrates are both meant to be quite important on the surface as well. And these are thought to be coming from the ocean below and onto the top of the ice. And I've sort of started to break this down in terms of Lego bricks, in terms of how the crystal structures are put together, especially with magnesium sulfate hydrates. They have this very sort of octahedral unit going on there with the magnesium bounded to the six water atoms, and that's sort of a feature. Magnesium sulfate hydrates are known to have a number of forms, so everything from a monohydrate through to well, the 11 hydrate, which I can never remember, it's undecahydrate, and some of these actually have mineral names because they're found on Earth. So one of the things I did as an experiment was to start to think, well, if we do have these magnesium sulfate hydrates and sodium sulfate, but we'll just talk about magnesium sulfate. If we do have them on the surface, but they're then being, you get sulfuric acid adding to this from the exogenic. So what's happening when you mix endogenic and exogenic features and processes on Europa? Is this going to change? Is there going to be a dominant material come out, or is this going to drive sort of mineral diversity on the surface? So we looked at the ternary, and we actually, I'll just show you sort of stepping through the diffraction of just one composition. So there's just this composition here. So we crystallize it and we get sort of glass and water ice. And then as we go up, so this is, each of these is, what I've done here is I've stacked the diffraction patterns in terms of temperature up there. We then get 2 hydrates of sulfuric acid form, but also a hydrate that I couldn't identify at the time. And then we, one of those hydrates melts, and then we get more ice coming in there. Here we've got 2 brand new hydrates form at this point as we're going up with temperature. So all it's doing is this is just a mixture of magnesium sulfate, water, and sulfuric acid. But you can see how many different materials are popping up. We warm up again and we get magnesium sulfate 11, so that's the mirabolite structure, but yet again another new hydrate appears. And then again later on you can see that they've all got different melting temperatures, different physical properties, and this leaves us with just that one new hydrate. And the nice thing is, because that left us with a pure pattern, we could go on and solve that. So the moral of that story was that it's all very well sort of analysing the spectra from Galileo and from the European service in terms of sort of simple materials, just sort of one hydrate or another. But in reality, we're likely to have a mixture of both exogenic and endogenic processes. And so those are really going to drive some mineral diversity on the surface of Europa. So that's a sort of a bit of a warning system, but there's a lot of complicated and interesting structures to be found there. So stepping out, we'll go further to Titan. And a lot of my work recently has been focused on what's going on in Titan, and as probably many of you know how interesting it is. It's the largest moon in our solar system. Well, it was nearly the largest moon. Unfortunately, its atmosphere sort of inflated it a little bit, and actually turns out Ganymede is about 50 kilometers, a little bit bigger. But one of the things that the Cassini mission has really revealed is that it's a whole different chemical inventory, and there's a massive potential for different chemicals going on, and different planetary processes, and as a result of that, of course, potential of astrobiology happening. I think Carl Sagan once referred to Titan as a potential prebiotic chemical laboratory. So one of the big surprising discoveries from Cassini was that water ice, it wasn't as abundant as they thought, and they really did think, I think everyone expected it to be sort of like the Galilean moons, and actually there's a lot of these smaller molecules carpeting across the surface. Now, why is that? And that's because of that atmosphere again, which is principally methane and nitrogen, but you get they get radicalized by the solar wind and the energy from Saturn, and these cause bigger and bigger molecules to get formed as a result of this, and then they all rain down on the surface. And as you can see, there's a number of astrochemical models that sort of follow this through, and they've come up with different sort of calculations for the flux on the surface. But the upshot is that there's this big list of molecules that we now think are on the surface, and that are what are actually shaping the surface there. So we went forward and started looking at what was known about, so it's like we know a bit about the chemistry, what about the materials, and actually there's a really big database of chemical crystal structures called the Cambridge Structural Database. It has over 1 million crystal structures, but bizarrely I could only find about 50, maybe only 30 to 50 that are relevant to Titan. And through that I then went forward and sort of classified them a little bit in terms of what they could what they would be. So we have everything from sort of gas hydrates on the surface there. So the gas hydrates are those water clathrate structures, and we think that they're very much at the sort of bottom of this layer where the water has integrated with those hydrocarbons, and you get those hydrocarbons forming in those cages there. We then also have the co-crystals, and I'll talk a bit more about them. And then, of course, there's the likelihood that these these phases will exist pure on the surface as well, so as molecular solids. So a lot of this work was started by the Planetary Ices group at JPL, and this is where I first got involved. And they were on the hunt for what could be an evaporite mineral on Titan. And that came off sort of the radar imaging from Titan that showed that not only did you have little lakes, but you also had dried up lake beds as well. And I like to point out that these are quite analogous to what we can see as you fly across Australia as well. Unfortunately, with Australia, you know, I couldn't land the plane, but I could actually walk up and grab a bit of this and take it to my lab and work out what it is. Obviously, we can't do that on Titan just yet, although quite looking forward to Dragonfly getting there. But of course, the temperature on the surface of Titan is around minus 180 degrees C. So this isn't going to be a water evaporate. So what can sort of evaporate and leave behind a residue? And the group there had looked at benzene. So here are some beautiful benzene crystals. And when they flood it with ethane, which is of course a known material in the lakes of Titan, you can see that there's quite, just by looking at it, quite a big change. Those crystals get sort of gobbled up and broken up. And then they looked at this with the Raman scattering and saw some big shifts in the Raman as well. And then they came across to Australia, and we recreated that same experiment, but in a diffraction sense. So this is the simple benzene structure. We add in the ethane and suddenly, whoo, big change, and a new form there. And this data again was from the Australian synchrotron. Were so good that we were able to solve that crystal structure, and it's a benzene ethane 3-to-1 co-crystal. The really beautiful thing is this really lovely framework of benzene with ethane living down the channels. And one of the lovely things that I got really excited about is a group based at the Southern Methodist University in Texas have actually found another one of the family. In this case, it's acetonitrile that lives down the channels there. And so we've already got a potential sort of framework family going on, and we're going forwards and trying to find a few more. But of course, Morgan, Cable, and Chuan Vu have carried on screening for more and more of these co-crystals and been very, very successful. We now know of about well, 6 for sure that we have diffraction patterns and things for, but there's a couple of others that we're beginning to theorize. We're working a little bit with theorists on this as well. And even then, we're able to start even grouping these co-crystals. So these are 2-component materials. So we have from layers, we have chains, and we have frameworks. So we're already seeing a big change in their crystal structures, but of course this impacts onto their physical properties as well. And I'll just say we've just published a nice paper in Accounts of Chemical Research about all of this. So yeah, so that's all great, and I've got sort of a sort of graph showing the sheer potential of this work. So along here is all of those materials that that the astrochemists and now actually the astronomers are more and more thinking are on the surface. And then in the boxes I've sort of put where we know the density of a co-crystal between the two of them. And then of course down in red is the pure structures. Hang on a moment. You can see that there's some missing information there. I would have thought by now in 2021, we would know the crystal structures of all these simple molecules. Well, it turns out that we don't. And in some cases, there's actually a good reason for this. Things like hydrogen isocyanide is more of a sort of astrochemical model and molecule, and is one of those things you can't just buy from Sigma Aldrich or Merck and put in your laboratory. And some of them are quite unstable on our lab bench timescales. But some of them, propadiene, propyne, butene, butadiene, are all actually quite accessible. And I'm still surprised that no one's ever just sort of crystallized them and seen what happens. So that's sort of low-hanging fruit, and one of those things that I've been doing with our neutron diffraction, because we don't necessarily need really high resolution diffraction to solve these. And I should also say, some of you who might know a bit about neutron scattering are like, oh, surely she's using the deuterated equivalents. I don't, because Wombat is such an awesome instrument, and I'll show a good example of that I actually can use hydrogenous materials with it. And I should say that even ones with published crystal structures have been a bit interesting. I've put here the example of acrylonitrile. Acrylonitrile is sort of a very nice simple molecule, and it was predicted back in 2015 to start being able to form membranes. But it's interesting, and I'll come back to that in a minute as to why that is a bit interesting. So I've actually been going through and doing probably a little bit of stamp collecting, but filling in those blanks. So we've recently solved the structure of butadiene and propyne. Interesting, butadiene, this is a bit of a crystallography nerd thing. It was actually first at least suggested, or at least the unit cell was discovered. So the box was suggested back in 1940 by somebody who actually worked at the lab that I worked in briefly in London. But it's interesting that we've actually found that it's a smaller unit cell, and so it's a little bit more simpler to describe. So there's a lot more of this work to come, and it's quite nice. The crystallographers as a group really love it. It sort of harks back to some of our history and things like that as well. But as I said, even for known crystal structures, so acetonitrile is probably one of the most used solvents in any lab, and there are numerous crystal structures in that database where it's sort of there as a co-crystal, or it's there as a co-former as well. But we looked at it pure, and again, they already knew the crystal structures of it, sort of monoclinic and orthorhombic crystal structures. We did the neutron. Neutrons are generally with bigger samples. Everything was kind of expected. But when our honours student, James, went to do it on the X-rays with a smaller capillary, he found that as he cooled down, he actually got the high temperature form persisting at low temperature. And then when he warmed up, he would get the low temperature form, and then he'd get a mixture of them all. And so what he discovered was that actually we've got the potential of phase trapping. And again, this is seen in earth minerals. So cristobalite, which is actually a high temperature form of silica, of quartz, that cools down too quickly. So a volcano erupts, it cools down too quickly, and it becomes metastably trapped at our room temperature. And it's one of those things that we can use as, go out in the field and actually find and use it to sort of say, hey, there's probably been a volcano around here. So we've sort of suggested that this is a potential marker for Titan in that same context as well. And I mentioned about acrylonitrile because it forms those membranes and things. We actually only know of one crystal structure of it, and that crystal structure is very disordered. And it's actually this that's sort of gone on and people have used to form that membrane idea. I would be a little cautious of that because that you don't really understand sort of the energy landscape around that molecule in this sense so well. And so one of the things I've been trying to do is find the ordered form of this and be able to then work out if that would impact on our knowledge of those membranes. One of the things that I've discovered as we've done this, though, is that I think we get phase trapping again. So I actually think that this beta form, so this we've started naming it, this alpha form is that same disordered high temperature form. We've discovered this beta form, which I believe is the low temperature form, but the awkward thing is we get the alpha form forming at the low temperatures as well. And the interesting thing is this has happened in our neutron diffraction data. So this is a much bigger sample. So with the acetonitrile, we hypothesized that the phase trapping was happening because of sort of strain from this really tiny capillaries. The capillaries we use for that are only 0.3 millimeters. In this sense, this is both a disordered thing, whereas acetonitrile is not disordered, but also it's happening on a bigger sample. So the mechanism of this phase trapping is very different. So that's something that we've definitely got to delve into a bit more. So last stop, and I'll whiz through this a little bit to allow time for some questions, is a stop by Pluto. And I've been, as I imagine many of you were, absolutely fascinated when we saw those New Horizons images of all those beautiful glaciers on Pluto. And those glaciers, as we know, are mainly made out of nitrogen and methane. Now, for me, nitrogen and methane are very interesting solids, especially methane. It's actually the reason I'm shows it all a bit bonkers there is because it's actually in its solid phase, it's actually rotationally disordered, and the same actually for nitrogen as well. These means actually, and I don't know if you've ever frozen a piece of nitrogen and stuck it on the bench. I have. It's like jelly. And so these are what we call plastic solids, and they're quite unique, and I don't think has really fully explained how they're going to work on a sort of mechanical rock situation just yet. But I noticed that we sort of didn't, no one knew the thermal expansion of nitrogen and methane sort of over the Pluto seasonal variation, and I should say that that's a relatively straightforward experiment for me to do. And one of the reasons for that is because we've adapted sort of these gas delivery sticks, so these go into our cryostat. They were originally designed to do gas dosing experiments for metal organic frameworks, so I've sort of appropriated them to do some planetary science. And so it means that I can condense things like methane and nitrogen all the way down to around 5 Kelvin or so without too much trouble. And so I was able to look at methane, and again should say that this is hydrogenous methane. So we do get a larger background, which is why the data isn't going to be as pretty as the nitrogen data I'm going to just show you, but you're still able to track the unit cell, and you can see that this jump here actually equates to a phase transition that's known. This is the phase 2, and then it jumps to phase 1. So that's sort of less interesting in a way because that's not during over Pluto temperature scales. But nitrogen is perhaps a little bit more interesting because it does have a phase transition over sort of the seasonal variation of Pluto, and just in this work we were the first to sort of classify that density change. And you can see we go from the sort of disordered high temperature beta form to an ordered alpha form as we cool down. And actually, this is a sort of, again, you'd have thought by now we should know what the crystal structures of the elements are. No. It turned out when I collected this data, and I was actually quite surprised at how beautiful it was, that there was actually a long-standing controversy on the crystal structure. It's very subtle. It's around where these molecules are actually centered on the origin. So the pervading structure had them sort of slightly off-center to the origin, and the structure that I've kind of proven it has to be is actually centered. It's actually quite important because if you have this uncentered structure, it actually imposes a sort of pyroelectric properties onto the nitrogen, which could have been very interesting, but unfortunately, unfortunately, I don't know, fortunately for Pluto, we found that it's actually more the simple symmetric structure. And there's some of the information as to why that is. And it comes down to there should be peaks here and here if it is the asymmetric structure, and there just isn't those peaks. But one of the things that I thought it was interesting that this work sort of exposed was quite the contrast in density. That methane really isn't dense in any way compared to like nitrogen and water, and just here we've just sort of the thing we're able to show is how that density changes over the temperatures, and also the disparity between them as well. So yeah, in this hopefully summarize what I've talked about. So hopefully I've convinced you all that cryomineralogy is a largely unexplored field. So we're very much at the stage of just trying to find the crystal structures. And despite how simple the materials seem to be on first glance, there's an awful lot to do. And I talked a bit about Europa and showed how we think radiolysis and the both endogenic and exogenic processes have expanded the range of materials that we would expect on Europa. I've talked a bit about the upper atmosphere effects on Titan that would lead to a big inventory of molecular mineralogy. And lastly, you know, would a glacier on Pluto be good to ski on? Still got to work it out. It certainly would be wobblier than going into the slopes anywhere else. With that, I'll look forward to your questions.
Thank you, Helen. I don't know if you can hear it, but there's clapping in the room.
Yeah, cool. Thank you.
I am hesitant to unmute things, but are there, I guess I've locked things, so we should be somewhat safe. Maybe if there are questions, someone could raise their hand in Zoom, and then I could unmute you to ask it. Blake Rogers, is that someone? Okay. Okay, great. Sorry, Blake. Okay, I'm trying to unmute you, Blake.
Yeah, can you hear me?
Yes, great.
Oh, perfect. Yeah, I was in regards to the acetonitrile and was it acrylonitrile?
Mhm.
I was wondering, do you have like the ingot structure forming where you have dendrites flowing into the surface or coming from the surface and going into the core of these? I don't know if you're doing it in a capillary tube or whatever,
Mhm.
but do you think that could be causing some of the high energy kind of or what would you call it?
This
Yeah,
the phase
high end.
trapping that we're seeing.
Yeah, do you think that could be
Hmm.
something maybe?
Yeah. So yeah. So it's a good point actually. So yes, the way we form these is that I'll just bring back the acrylonitrile work. So with the X-rays, you're right. We have really small capillaries and we condense the material in. But sort of once we've condensed it in, we sort of keep it there. So which is why we thought that when we got the phase trapping in the acetonitrile, that it was coming because sort of like there was strain accumulating around the walls of the capillary,
Mhm.
and that the core of the capillary, the sample there was less strained, and it was that was causing the issue. With the acrylonitrile, we're actually doing this in a large 6mm vanadium can. And so there we don't think that strain's going to be occurring and stuff like that. But yeah, certainly, I mean, the powder diffraction, it looks pretty average. So like as in, we don't see big texture changes. So I don't believe that there's like just one long crystal forming along it. So which, as you're right, could definitely have formed things. I think we're still getting good powder averages of the thing. So yeah, I've definitely something to consider though.
Perfect, thank you.
Just gonna go down in order here. Jake, you want to go ahead and ask your question?
Yeah. First of all, thank you for the talk. This isn't really my sort of field, so I apologize if this is a really simple question. But you mentioned that they sort of had like this lookup table for all of these materials that you were looking at, but then you said you were finding like the discrepancies kind of between when you were measuring. Does that mean that when you go through and you're trying to compare these, are you having to remeasure every single one of these materials to try and make sure that it's not actually something new, it's just something we never measured before, like that we should have seen already?
Yeah, there's definitely a bit of that. So the Cambridge Crystal Structure Database, which is the one that I searched, it's like, as I say, an inventory of about 1 million different crystal structures, but each of those crystal structures are only determined at particular conditions. So some of them in terms of pressure and some of them in terms of temperature. And it's pretty common to have a lot of them, especially these sorts of materials, only determined at, I know, 130 Kelvin. And that's because most crystallography labs, that's where they run their cryostream, and that's where they run. So not many labs, and this is one of the reasons I'm finding differences, is sort of originally people only approached looking at these materials from a crystallographic sense. Sometimes there's curiosities. There was a whole group who looked at, they were interested in what would be weak interactions that hold crystal structures together, and actually they're the ones who discovered a number of the co-crystals that we look at, especially this one, the benzene, oh, what's that molecule, the long molecule, it's in torches, benzene acetylene, and that one is particularly weak, and it's actually kind of amazing how it holds together and stuff. So part of a lot of the differences and the things that we're seeing is just that no one else has ever looked at them at varying temperatures, because there wasn't the scientific motivation before. And even just looking at things at 90 Kelvin, which of course Titan is kind of nice, you always know how to dress for the weather there. You know, even just because these materials are often very highly disordered, that difference between 130 Kelvin and 90 Kelvin can be the difference between an ordered and a disordered crystal structure. So yeah, it's sort of, I suppose the other thing is there's a big field of crystal structure prediction. And I've talked to a few of them a couple of times about, well, why can't we just predict acrylonitrile and work out what it is. And they sort of, one of them went back and he threw back a load of potential crystal structures at me. He threw back about 100 at me. And I think, again, it's that problem is the weak, the very subtle interactions that are causing there to be, because they're so weak and so subtle, we don't necessarily have a handle on how they all work. So yeah, there's a lot of work to do.
Thank you so much.
No worries.
Excellent. Stephanie?
Fantastic. Thank you so much for a nice talk. So I've got
No
a
worries.
couple of questions. I'll try to keep them quick. You're mostly doing powder. I'm more familiar with single crystal myself, so I assume you're doing some sort of Rietveld refinement to take you from your powder structure to your predicted single crystal, I'm doing inverted commas in midair sort of thing. Have you done any of the back confirmation, grown some single crystals to confirm what you're seeing?
Not yet. And I suppose the thing is, yeah, I mean, my sort of thing has always been to do to do structure solution from powders, and I would sometimes, yeah, so we're doing Rietveld refinement. We often do simulated annealing to begin with to come up with some models, and then we go forward and do the Rietveld. I sometimes would argue that powder diffraction or crystal structures from powder diffraction could potentially be more representative of the bulk than single crystal.
Sure.
I mean, yeah, we're certainly missing out on the really fine details, and certainly like hydrogen positions could be, especially in some of the really subtle things, could be very important. So certainly, but we can go forward and compare the structures. But I mean, I did do a nice refinement of the acetonitrile structure, because those ones, both of those have been determined from single crystal.
Sure.
And then when I did the refinement, they matched up really nicely. So yeah, it's not something that the reason I probably would grow the single crystals, just because I'm a bit lazy. It's a bit difficult to grow single crystals. I would probably do it, and I would use one of our neutron. We have a neutron single crystal instrument called Koala, just to really, just to really understand how these molecules are holding together and things like that. So that's probably going to be a motivation down the track.
Sure. Any thoughts on looking at tholins or something like that?
The difficulty I find with tholins is that from reading quite a bit about it, is it's hard to pin down what they actually are.
Yeah, that's why I thought the powder might be the way to go with that.
Yeah, certainly I would be fascinated to get a sample of some of the work that some of the tholin samples that people do, and just to look at it and to see what crystallizes out. It could be that a lot of it is kind of glassy, amorphous, but we could still get some, changes and structural changes out of that. I would imagine that it would be a mixture, that there would be some crystalline phases, some amorphous phases, and we could fingerprint those if nothing else. That actually would be a really nice sort of APS mail-in, is to put it in a capillary and send it there and see what happens.
There you go. Thanks for that.
No, no worries. Thanks.
Anna, go ahead.
Okay, there we go. I thought it came up saying I had been unmuted, but I guess I was just allowed to unmute myself. Yeah, that was a really cool talk. Jennifer and I are going to be looking into this phase trapping a little bit more.
Awesome.
But I have a pretty simple question. I think I missed it. So with the sulfuric, hexa, and octahydrates, with what you had determined, is there an indication that it is on Europa, or are we off the octahydrate and it's the hexa, or yeah?
I don't think we know yet, because
Okay.
and I haven't. It's kind of bad on me, is I actually got a near infrared spectrometer to try and do a fingerprint of it, but I don't think anyone's actually collected a fingerprint of the hexahydrate yet. And one of the difficulties is it's always mixed. It never occurs on its own. So being able to find a sort of definitive fingerprint that this is sulfuric acid hexahydrate and this is sulfuric acid octahydrate is going to be really, really challenging. And it's one of the reasons that there's a whole paper of does sulfuric acid octahydrate even exist? And that's from spectral data it's back in 2008 or so. And it's just because they were getting confused, because I'm pretty sure they were getting both phases crystallizing out. So yeah, I suppose it just goes to show that we need to consider this. We've got libraries of spectral data, but we do need to consider the potential of metastable phases that will be there, and we can't necessarily pull them out. Yeah, it's certainly something to talk to the spectral people about.
Cool, thank you.
No worries. I should say I've actually got NIMS data behind me. NIMS took a picture of Australia, and the reason I really like it is, hang on, which it's this side, is because you can see it took this picture at 50,000 kilometers. And you can see that fuzzy blob there. That's the Great Barrier Reef that
Oh,
you can see.
wow.
It's the calcium carbonate for it. So I really love this image.
We are at
Nice.
5 o'clock, but Jorge has had his hand up for a while, so we'll let him go and then I'll cut it off at that point. I will just say that Helen is wonderful and really friendly. So if you have questions, you should send her an email and
Yeah,
start up a
absolutely.
conversation.
Please do. I'll just leave up my contact details.
Okay, Jorge, go ahead.
Hello.
Hello.
Hi. I very much appreciate your talk. And also I wanted to comment on how much I appreciate you sharing some of your previous talks on YouTube. It's helped me out quite a bit. And I've come to enjoy this very much, looking into the stuff that you've shared with us today. And I wanted to ask regarding the Excel spreadsheet, the one that says quite a lot of work still to do. I thought I remember hearing that you had mentioned in a previous talk that one of the disadvantages, or well, one of the issues was that even if we were to find values for those missing cells in, the values in the spreadsheet, that we would still be missing the crystallographic structure or the crystal structure. And I was wondering if you would comment on whether or not it would be useful for theoreticians to have artificial intelligence type of algorithms that would highly, with high accuracy predict the properties that we were seeking, if that would be something that would be useful or not.
Awesome. Oh, this is a great question. And yeah, so I'll bring up that again. So yeah, the numbers that I've got in there, I didn't explain particularly well, sorry. They're all the densities of the different materials at, I think I normalized them all to be 100 Kelvin and standard atmospheric pressure. Just knowing the crystal structures would enable us just to fill in all those numbers. That's sort of like one of the key sort of great bits of information. But yeah, that's been one of the and certainly with some of those astrochemical molecules, ones that are going to be really challenging both experimentally and safety to do experiments on hydrogen isocyanide. And it's a very simple structure. So I know the crystal structure prediction people are using things like machine learning in order to try and predict structures. But there's a lot of challenges going on there. And I should say, yeah, and the point you pick up on is it's sort of my hope would be that once we know more about how the pure structures are holding together, then we can use that information, the sort of the intermolecular forces for each one that's typical for each one. We can then feed that into things like AI into crystal structure prediction to be able to fill in all these other boxes. So, and to be able to say, yes, there will be a crystal structure forming between these two co-formers, or no, there won't. So that's sort of where we are with the co-crystal work. And I should say, this is only 2 component systems, of course. These are only binary systems. We've already seen indicator of a ternary system that's a co-crystal. So yeah, it's sort of slightly scary how much there is to do, but we'll get there. We'll get there.
Okay. I know there are more questions. You really want to ask yours, Rob?
Well,
Do you mind hanging on a little bit longer, Helen?
I'm not going anywhere. I'm in lockdown here in Sydney. So.
do I speak anywhere?
Yep.
Okay. I'm Rob Wetton here, NAU. And I was very interested in your comments on, but I couldn't always tell whether you were using neutron or X-ray. For example, the hexahydrate or octahydrate of sulfuric acid, I believe I heard you say quite confidently, it's hydronium, and I guess that means bisulfate. And I recall working with a diffraction specialist, another British neutron guy, and looking at the crystallography of that, and he said, you cannot determine from the crystallography that the proton is transferred so that it's really an ionic hydrogen bonded solid versus a neutral. Although chemical and physical guidance would tell you for sure it's an ionic solid, you know, it's a hydronium. So I just thought maybe you could just say, was this a case where you absolutely needed neutrons to find the 3 protons around the oxygen for the hydronium, or not?
Yeah, I'm sorry about that. And part of that is because I actually use both together a lot of the time. And yeah, in the case of the octahydrate, we first determined sort of the heavy atom structure from the synchrotron. And then actually it was my first experiment where I'm currently working now. And I was actually came as a postdoc, and it was quite good because I met a lot of people and ended up with a job there. But yeah, so I did an experiment on echidna with the high resolution neutron diffraction that we have here. So, and you're right, it is proton positions from powder diffraction can be a little bit difficult to determine. You can probably see, I can direct you to our, have I got the reference to it? The Journal of Applied Chemistry paper where we discuss it quite a lot. So yeah, in this paper. Oh no, I haven't got a reference to it. I do. Oh no, it is in that paper. Sorry, it's not. It's in the Journal of Geophysical Research paper. And we do present both the neutron and the X-ray diffraction data, and we show the models that fit both. So it was pretty essential in this case for both the hexahydrate and the octahydrate to have both the neutron and X-ray diffraction to determine that.
Thanks for pointing out the actual paper. We'll look it up. This is actually a question in atmospheric cryomineralogy, if you will, because cloud condensation nuclei in the pristine southern Pacific, like you know, are trying to form these little crystallites of sulfuric acid and water. And real quick, you didn't mention electron diffraction except right at the very start, almost to dismiss it. And I wondered if you were aware that electron diffraction of jets, of supersonic jets, so forms very nice little microcrystals. Thermometry is a little bit of a challenge, but running an electron beam through a jet of microcrystals of molecular and ionic solids, very much like you're showing, is a wonderfully rapid and sensitive way to get a powder pattern, which, you know, the Rietveld method may or may not be able to and so are you sure there's no competitive activity? Because that would be very high.
Yeah, no, I'm sorry for being dismissive about it. It comes of when you're dyed in the wool with using 2 techniques, and you're also an instrument scientist that runs a neutron instrument, and you want to keep your instrument as relevant as you possibly can. But yes, I mean, the future is incredibly bright with things like the free electron lasers and cryo-EM. I've seen some really interesting papers of using cryo-EM, which is more imaging really, to determine small molecular structures. So yeah, I shouldn't be so dismissive, but I suppose from my point of view, from the sort of mineralogy standpoint, we do want to look at, you know, changing the great thing about the instruments that I use is we're all about changing the conditions of the material. So it's all very well determining the structures, but also we want to change and see how the structure responds. And I think with a lot of these new techniques, that's not so clear just yet. As you say, there's some temperature control challenges and things like that. But yeah, certainly down the track for sure.
Great talk. Thanks.
No worries. Thanks.
Thank you, Rob. Since we're still going, I'm just going to give Jennifer a chance to ask her question, and then we'll wrap it up at that point.
No worries.
Okay, Jennifer.
Thanks. So at the beginning, you talked a little bit about chlorine salts on Europa, and I'm just curious if you've done any work with those.
Not a great deal. I did a little bit just to look at how they might repair. So there's just to look at sort of the how the color centers that form in sulfur in sodium chloride might repair as they go on, as they're exposed to sort of more visible light. And one of the interesting things, it did show that they actually repair quite quickly. So I'm not totally convinced on the explanation of the color centers being the formation of the orange bits on Europa. Yeah, we have done a little bit of work with some potential ocean compositions, and of which sodium chloride was a part of that, and things like hydrohalite and things like that was a crystalline feature. One of the things actually, and sort of that work got really complicated, and we didn't quite get too far with that. The one thing we have done a bit recently, and this was with Baptiste Journeau up at University of Washington, is that we've started measuring the density of states of a lot of these hydrates. So actually hydrohalite was one of the ones we started with, because that would enable him to, because he's doing some wonderful calculations of all the thermodynamic properties based on the crystal structures, but he also needs the density of state measurements in order to pin down the thermal contribution. So we've started, and it's been a new world for me, doing a bit of inelastic neutron scattering, but it's sort of one of those things that when you have it on site, I've been using our Taipan instrument for that. So I'm hoping that if I get the sort of methodology of that set with some of the hydrates, and they're actually pretty challenging because there's complicated structures, lots of things going on.
Aware.
Yeah, so it would mean hopefully that we could then apply these to other cryominerals as well.
Great. Yeah. So I've done some Europa work too, so we should talk about that more.
Awesome. Always happy to. Although I don't know, there's part of me that went to Titan because I got so freaked out by hydrates and how complicated they were.
Yeah, they're pretty complicated.
Yeah.
Well,
Okay.
thanks.
No
Thank you
worries.
for all of the questions. That was great. Thank you, Helen. I'm really impressed by how you recovered from such a rocky start. I would not have done that so elegantly. So yeah, thank you one more time, Helen. This was really wonderful and interesting and thought-provoking. I'm gonna have to send you some questions offline because we're obviously a little bit over now.
Yeah, no
I would
worries.
just like to finish by saying we're gonna have another seminar next week. Mariana Potkova is gonna be joining us virtually again, but joining us from the University of Illinois at Chicago. So please join us next week. Thank you again, Helen, and goodbye, everybody.
Cool. Thank you. Take care, everyone.